All right, so today we're going to be talking a little bit about scatter plots, which is chapter 12. And in particular, we want to look at what a scatter plot is, kind of describe how you would build one, and then what we can do with scatter plots when it comes to using statistics. So I'm going to start right off with an example. A scatter plot is a graph where there are dots scattered around the graph that describe individuals from the population or the sample that you're actually studying. So each dot represents an individual, and that individual is going to be measured with two variables. So we can see on this scatter plot that we have the highway, or miles per gallon. Highway miles per gallon is the first variable, and city miles per gallon is the second variable. And so it looks like our individuals in this particular sample are cars. So when I look up at a car, an individual car, so here's an example of a dot, I can see that this corresponds to, it looks like about 48 miles per gallon for highway, and it looks like it corresponds to about 50 miles per gallon for city. Each of these dots corresponds to a different car who's measured on two different variables. Now, if I'm to build a scatter plot, this is essentially what I'm going to do. Is I'm going to give it a title, whatever I'm describing. Here I'm trying to talk about the difference between city miles per gallon, highway miles per gallon. I'm going to label the axes, so highways miles per gallon and city miles per gallon. I'm going to give it a nice x-axis and y-axis, and then I'm going to draw those dots in. And so then once I draw those dots in, this gives me a nice scatter plot. I will mention a couple things. One is on this particular scatter plot, one thing that I'm not particularly fond of is down here at the y-axis, the 10 looks like it's sitting on 0. And why that's problematic is because it makes it look like there are certain cars that get practically 0 city miles per gallon. The same thing, the 20 is not too far off from 0. And so it also makes it look like these cars are kind of coming closer to 0 than they actually do. If I was to draw this scatter plot, then that first value of 20, so if that's sitting at 20, so I'll go 5, 10, 15, 20, 25, 30. If I went up by 5s, and then if I say I went up by 10s on the other one, 10, 20, notice what I'm trying to do is I'm trying to give it a nice even increment for my hash marks on this particular scatter plot. What that does then is it makes the first one look like it's actually sitting at about 13, so that'd be up here, and it looks like it's sitting at about, let's say, 10. So that first dot would actually be sitting further away, be pushed further away from the origin of this graph. If you do have an issue where the numbers that you start at are very large, much larger than 0, my suggestion would be to take your graph and put in this little lightning bolt type thing to show that you've crunched that part of the graph, and so that people know that it's not being misleading. Otherwise, the scatter plot is pretty good. It gives us a good idea as to what's going on with cars. And we can actually start to see a relationship between those two things, the highway miles per gallon and the city miles per gallon. We have two variables when we look at a scatter plot. Both are quantitative. We have an explanatory variable, which we put on the x-axis. So the x-axis is the horizontal axis. So that's the horizontal axis. And the response variable we put on the y-axis. That's the vertical axis. So if we're looking at a graph, we have that this is the y-axis and this is the x-axis. The explanatory variable is the independent variable who actually describes what's going on to the response variable. So as it changes, it causes the change in the response variable, if it truly is an independent-dependent relationship. And that's part of what we're going to look for when we're looking at scatter plots. The response variable then is the one that actually responds to the explanatory variable. It changes in response to the explanatory variable. And the idea here is that if you have something that explains something else, you put that something that does the explaining on the x-axis. So for instance, age and height. As you grow, you get taller. at least what you do generally when you're a small child. And so you would put age on the x-axis and height on the y-axis because you want to have that age explains height. And so this would give you how the variables show up. On the previous slide, we saw that the x-axis was city miles per gallon, the y-axis is highway miles per gallon. One doesn't really explain the other, although there still is a relationship between those two things. So in some situations, it's difficult to pick out which one is the independent or explanatory variable, but if you can, put it on the x-axis. When we talk about scatter plots, one of the things that we like to do is measure how closely one of the variables has correlation to the other variable. So are these two things related? And typically when we're talking about related, we're going to be talking about a linear relationship, meaning that do these dots fit a line? So the way that we can describe this is using what's called the correlation coefficient. The correlation coefficient is a number between -1 and 1. And we look to see whether or not the dots on the scatter plot fit closely to a straight line. And if they do, that correlation coefficient is going to indicate that. Now, the dots may be going up from left to right. And if they are, then we would say that it's a positive relationship. If they're going down, we'd say it's a negative relationship. The R value closest to 1, a positive 1, indicates a strong positive correlation. And an R value close to -1 would indicate a strong negative correlation. And then an R value in between -1 and 1, the closer it gets to 0 would imply that there's no correlation. And so the question is whether or not it's fitting a line. Now, if it fits a line, that tells us that these two, and there are other curves that you could try to fit, but the ones that we'll be concerned with would be a line. But if it fits a line, it tells us that these two variables, you can use one to predict the other, which is really quite nice. So let's take a look at some examples. So this first one where we had highway miles per gallon and city miles per gallon, it does look like it fits a line. So if I draw a line straight through these points, most of those points are very, very close to that line. And so the correlation is going to be a very strong positive correlation. I would say that R is approximately something like 0.9. I do not want to say that R is equal to 1, because R equals 1 would imply that every dot is actually on the line. So R approximately equal to 0.9 still tells me that's a very strong positive correlation. And it's positive because it's going up from left to right. In other words, the slope of that line is positive. If we're looking at the next one, where we have driver's age and the maximum distance to read a sign, it looks like a negative correlation. So if I draw the line that goes through this, it looks like it fits a negative correlation. Notice that a lot of the dots are kind of spread out, and for that reason, not all the dots are fitting the line nicely as they were in the previous example. So maybe R is approximately -0.75 or something like that. Now, I don't actually know the true R values here, but I'm trying to make an approximation. And I'm trying to indicate from the first one to the next one that the correlation is a little weaker on the second one. And you'll notice the last one, the dots are all over the place. Now, if you try to draw a line going positive, it almost seems like it might fit. But others could argue that the line looks like it's going sideways like that, or it looks like it's kind of going down. Now, either way, the correlation to be positive would have to be some positive number. If the correlation was negative, it'd have to be some negative number. Or if the correlation has a slope of 0, it would have to be something close to 0. How could you possibly fit a number for that works for everybody? It looks like R is approximately 0. That's the only way to really kind of talk about the correlation for that. And it's telling us that there's no correlation. In fact, this is measuring new chicken eggs on a farm compared to the number of ice creams sold. I don't even know how those could possibly go hand in hand. Although, strangely enough, something that does go hand in hand is crime and ice cream sold. And that's because crime is up in the summer and ice cream sold is up in the summer. And crime is down in the winter because nobody wants to go outside when it's cold. And ice cream sold in the winter is also down because nobody wants to eat ice cream in the cold. Although, I think ice cream is good any time of year, but you eat less of it at least. So there we talk about correlations. Now this line that we're talking about right here is a very special line. And the reason why it's so cool is because it allows us to make some predictions. In fact, if I want to know when I'm 55, the maximum distance I'll be able to read a sign, I can go up to this line and look over, and it looks like I'll be able to read a sign at about 375 feet. Now I have a pretty good prediction as to what I should expect at the age of 55. Whereas if I'm 35 and I go up to this line and look over, it looks like I'm 420 feet. So I'm going to lose some distance over the next several years, where I won't be able to see quite as far as I could before. Or if I buy a car that has 35 miles per gallon on the highway, I should expect that it probably has pretty close to 32 miles per gallon in the city. These lines are very nice because they allow us to make predictions. This line is so nice that we call it a least squares regression line. And the least squares regression line is the line that approximates that relationship. It's the line that fits those dots really nicely. And it's going to have y equals b naught plus b1x. b1 is going to be the slope, and b naught is going to be the y-intercept. So here's an example. An example would be something like maybe y is equal to 3 plus 5x, something like that. You'll actually have some numbers plugged in. Why this is so nice is now suppose that x is a variable like the weight of some critter, and then y is the height of that critter or something like that. Then now if you know the weight or if you know the height, you can use this line to make a prediction. If the correlation coefficient is strong enough, you can use it to make a prediction on the other variable. So suppose that you knew that the weight of the critter was like 12 or something like that. So then y would equal 3 plus 5 times 12. 5 times 12 is 60, plus 3, so it's 63. So y would be equal to 63. So it tells us that the height is 63, whatever we're measuring in whatever particular units. So the least squares regression line is a really nice line that makes it so that we can make predictions about one variable using the other variable. And in the next video, we'll be talking about how we can actually compute some of these things.